We're going to look at the graph of an exponential function, starting with a base of 2, a power of x, and no scaling factor, just by plugging in values for x. So 2 to the negative 3, 2 to the negative 2, 2 to the negative 1, 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3, just plugging these x values into this expression. I'll start with the easy ones. 2 to the 1 is 2, 2 squared is 4, and 2 cubed is 8. Then working my way over to the slightly more difficult ones, remember that anything to the power 0 is equal to 1, and that negative power makes it into a fraction. So the negative power makes us take the reciprocal and make the power positive. So 1 over 2 to the positive 1 is 1/2. 1 over 2 squared is 1/4. And 1 over 2 cubed is 1/8. Now I'm going to go ahead and plot these points. And see what the graph looks like. Looking at these numbers and at the pattern, I can see that these, as we go toward the left, these y values are going to keep getting smaller, but they're never going to become negative. If it's a power of positive 2, it has to stay positive, and therefore these numbers approach 0. And on our graph we can see that we have a horizontal asymptote at y equals 0. Over here on the right-hand side, I can see that the numbers are starting to grow fast. And I see the same behavior in the graph. So in the first quadrant, which we sometimes call Q1, what we'll see is rapid growth. We can also see that the domain is all real numbers. And we can see that the range is only positive values. It doesn't even include 0 because of that asymptote. So the range goes from 0 to infinity using a round parenthesis at 0, non-inclusive. So characteristics that we can observe from this: a greater than 1, this is an increasing exponential function. If the base is greater than 1, we have something that is increasing. The y-intercept is at 0, 1. That's because there's no scaling of this. And it's increasing fast in the first quadrant. We can think of that as having a constant doubling time. That simply means that the y values double for some constant increase in x. In this case, because the base is 2, that doubling time is 1. Or doubling constant, we could say in this case, since the x-axis doesn't really represent time. We also see that the x-axis is a horizontal asymptote, as we already observed right here. We can observe many of these same characteristics, though not exactly the same, by looking at an exponential function in which the base is a fraction between 0 and 1. So we'll look at the base 1/2, and the characteristics that we establish for this graph will apply to all exponential functions whose base is a fraction between 0 and 1, provided that there's no stretching factor, no scaling factor. So we're going to look at let's start with the easy ones. 1/2 to the power 1 is just 1/2. 1/2 squared is going to be 1/4. 1/2 cubed is 1/8. Anything to the power 0 is 1. And now when we apply the negative powers, it's again going to take the reciprocal, but taking the reciprocal is going to result in an integer, right? So 1/2 to the -2, I would flip it and then square. 1/2 to the -3, I would flip it and then cube. So I have the same numbers that I had in the graph with 2 as a base, but they're not happening in the same places, right? Not in the same order. And now I have a graph that looks like this. I still have the same domain and range. The domain is still all real numbers. The range is still from 0 to infinity, not inclusive. And now my characteristics, same y-intercept, we're decreasing in the first quadrant with a half-life instead of a doubling time. So now my y value is cut in half for a constant increase in x. And the x-axis is still a horizontal asymptote, but now this is for positive x values. The asymptote was for negative x values in the last graph. So it's simply a reflection about the y-axis of the graph that we just looked at.